The title of this paper is Analysis of L-shaped, functionally graded viscoelastic shafts with longitudinal crack under torsion. The current analysis is concerned with longitudinal fracture in an L-shaped, functionally graded shaft of circular cross-section. The shaft is located in the vertical plane. The right hand end of the horizontal member of the shaft is clamped. The vertical member of the shaft is supported also by a rotational spring located in the horizontal plane. The shaft is made of a material that is functionally graded along the radius of the cross-section. The material has non-linear viscoelastic behavior. There is a longitudinal crack in the vertical member of the shaft. The upper end of the inner crack arm is under angle of twist that changes continuously with time. Therefore, the vertical member is loaded in pure torsion, while the horizontal member of the shaft is loaded in pure bending around the vertical axis. For the crack, the strain energy release rate is derived. The time-dependent energy balance is analyzed for verifying the solution of the strain energy release rate. The influence of various factors like the shaft geometry, parameters of loading, variation of material properties along the cross-section radius, and rigidity of the spring support are studied. The load-carrying shaft that is treated in this work is shown in figure number 1. In section L3, the shaft is supported by a rotational spring located in the horizontal plane. This spring has non-linear elastic behavior that obeys the physical law number 1. In formula number 1, Tc is the moment in the spring, C is the spring constant, N is a parameter, phi L3 is the angle of twist of section L3. In portion L1, L2, the shaft hosts a longitudinal crack representing a circular cylindrical surface of radius R1 and length A. The upper end of the inner crack arm is under angle of twist, whose change with time is given by formula number 2, where beta and delta are parameters. The inner crack arm and the shaft portion L2, L4 are under twist, while the horizontal shaft member L4, L5 is under bending around the vertical axis. The shaft mechanical behavior under torsion is non-linear viscoelastic it obeys the law number 3, where tau is the shear stress, gamma is the shear strain, H, B, and D are material parameters. The behavior of the shaft member L4, L5 under bending obeys the law number 4, where sigma is the normal stress, epsilon is the strain, Q, S, K, F, and M are material parameters. The shaft is functionally graded along its radius. The variation of material parameters along the radius is presented by formulas from number 5 to number 11. The strain energy release rate for the crack is extracted from the complementary strain energy in the shaft by applying equation number 12. The complementary strain energy density in a shaft portion is extracted by integrating the physical laws 3 and 4 with respect to the corresponding strain. The shear strains on the surface of the portions of the vertical member of the shaft, the angle of twist of section L3, and the curvature K of the horizontal member of the shaft, which are used to calculate the complementary strain energy density, are derived by applying equations from number 14 to number 18. The strain energy release rate that is obtained by applying formula number 12 is confirmed by investigating the energy balance in the shaft. Numerical results for the normalized strain energy release rate are exposed in the next 3 figures. Figure number 2 shows how the normalized strain energy release rate varies when the value of the parameter beta of the angle of twist grows. The strain energy release rate beta curves shown in figure number 2 are built up at 3 H mu to H eta ratios to see what is the influence of the variation of material parameter H along the cross-section radius. It is evident from figure number 2 that both beta and H mu to H eta ratio have significant effect on the strain energy release rate. The strain energy release rate permanently increases as beta increases. Increase of H mu to H eta ratio induces reduction of the normalized strain energy release rate. The curves shown in figure number 3 indicate how the normalized strain energy release rate is affected by the spring constant C and the value of the parameter N of the physical law describing the spring mechanical behavior. It is evident that the normalized strain energy release rate can be reduced considerably by increasing the volume of C. Therefore, the longitudinal fracture behavior can be regulated effectively by using springs with appropriate rigidity. The growth of the parameter eta, however, leads to rise of the normalized strain energy release rate as indicated by curves shown in figure number 3. The change of the normalized strain energy release rate when K nu to K eta and L3 to R1 ratios grow is examined too. The corresponding curves are shown in figure number 4. The normalized strain energy release rate K mu to K eta curves are nonlinear for each of the considered L3 to R1 ratios, as shown in figure number 4. Besides, the rise of L3 to R1 ratio causes significant growth of the normalized strain energy release rate. Thank you for your attention.